So I'm very pleased to introduce Philipp Berghofer, who is a PhD student at the University of Graz, working with Sonja Rinhoffner on a PhD thesis where at least the original plan was to defend Ontic structural realism, that's my understanding, and that original plan got somehow modified, as it turns out. Philipp is here a visitor of the Space and Time After Quantum Gravity project. He works on epistemology, phenomenology, particularly the concept of evidence and philosophy of physics. He has an MA in philosophy and a BA in physics, and has funding from the Austrian Academy of the Sciences. So I'm very happy to have him here today. He will talk about Ontic structural realism and quantum field theory. Are there intrinsic properties at the most fundamental level of reality? Please, Philipp.
Okay. Thank you very much for this very kind introduction. So as has been mentioned, this paper that I will present today was originally, the original idea was to defend Ontic structural realism, but it turns out that I will argue against it. So again, thank you very much for this introduction. Also many thanks to the whole research group. It really is a pleasure to be here. Also hello to the research group in Chicago. And yeah, let's talk about whether there are intrinsic properties at the most fundamental level of reality. So basically, I have 5 aims in this talk. So at the moment, this thing does not work so well.
Sound is terrible.
Okay.
Yeah.
I have a complaint that the sound is terrible. Can we fix that?
So maybe if I'm closer,
No,
does this
the
make
sound
any
Is this
difference?
using the right microphone?
I think so, yeah.
Okay.
Is the sound better at the moment? So does this work, or should we? Do we have any input on this question?
Can you just check that? No, that's okay.
So maybe you should speak so that they can hear.
Okay, so as mentioned, basically I have 5 aims in this talk. The first one is that I will discuss different versions of Ontic structural realism, and then I will argue that the most tenable version and the most moderate version of Ontic structural realism reads as follows. Namely, at the most fundamental level of physical reality, there only are relational properties. Secondly, I will argue that in order to decide this question, we have to turn to quantum field theory. Third, I will argue that charge, mass, and spin of elementary particles are relational properties. So often it is assumed that charge, mass, and spin are intrinsic properties, but I will show that this is not true for elementary particles. But I will go on and show that it's true for quantum physics. So I will argue that, and this is my 4th aim of this talk, I will argue that fields are the most fundamental objects. So I will argue that it's not elementary particles, but fields that are the most fundamental level of reality. And finally, I will argue that fields do have intrinsic properties. And this combination of claims, namely that first it is fields that are the most fundamental objects, and secondly that fields do have intrinsic properties, this combination of claims means a refutation of moderate Ontic structural realism.
Okay, before we proceed, sorry, they can't hear anything at all in Chicago. There's a terrible echo on it.
Echo. Okay.
So is the setup? Is the setup the same the way we did
Yeah.
it always?
No, I think so.
But then you have to use audio or the.
Check the Skype settings. Is this the Skype
This
settings?
is a Skype setting.
But you're not on that one, right?
So this is this one. Microphone?
Yeah. Ah, yeah, okay. No, okay, you're right, okay.
I mean, this also shows that
Mhm.
they pick something, right?
Yeah.
So that seems to be the right microphone, right?
Yeah.
Yeah.
Um,
Okay, what about the speakers? Did we...
Why do we have this? Maybe
Okay, wait. Now? Is it better now?
we should not switch. We should completely switched this off, their sound.
So we now switch off our sound. So I think now they shouldn't have an echo.
Okay,
So, what do they say?
nothing yet. Sorry. Yes, it's better. Okay.
Okay.
go on.
Okay, so I should go on?
Yes, please.
Okay. So, as mentioned, this is the consequence. The consequence of this combination of claims is that, in my opinion, quantum field theory tells us that Ontic structural realism is refuted. So, let's have a look at the structure of my talk. As you can see, the structure is according to the aims of my talk. So let's just begin with the question of what is Ontic structural realism. The question of whether the world we live in is adequately described by our most successful scientific theories is one of the most important questions in philosophy of science. And concerning this question, there's a special focus on unobservable entities. So examples of unobservable entities are atoms, electrons, and quarks. And scientific realism is the view that we should have a positive attitude towards the existence of the entities posed by science. So we are justified or even obliged to believe in the existence of entities, whether they are observable or not. And scientific anti-realism is the denial of this view. So this anti-realism can be either epistemological or ontological. So in the epistemological sense, it is the claim we cannot know whether there are unobservable entities, and in the ontological sense, it is the claim there are no unobservable entities. The main argument and the most famous argument in favor of realism is the so-called no miracle argument. According to this argument, it would be mysterious how. So, according to this argument, scientific realism is the best explanation for the obvious success of our scientific theories, and this success would be miraculous if our most successful theories were misleading. And despite its initial plausibility, realism has been attacked on many fronts. And the two most famous arguments against realism are the so-called pessimistic need-induction and arguments for metaphysical underdetermination. So the pessimistic need-induction is the claim that in the history of science there has been a series of radical revolutions in which older theories have been replaced by new ones. And by induction it follows that our currently best theories will also be abandoned. And this claim goes back to Kuhn and Lauer. And the argument for metaphysical underdetermination rests on the Quine-Duhem thesis that no scientific theories and no unobservable entities in particular can be fully determined by empirical data. Now, structural realism has been introduced to reconcile these arguments. It has been introduced to be the best of both worlds by explaining the success of science but avoiding the pessimistic need-induction. And this structural realism in its modern version goes back to John Warren. And basically, it is the claim that what we ought to believe in are not the unobservable entities posed by science, but the structural content of our theories. And it's important that with respect to structural realism, we have to distinguish between an epistemic version and an ontic version. So the epistemic structural realism tells us that all we can know is structures, namely relations between things, not the things themselves. And ontic structural realism tells us that all there is are structures. There are no things in themselves. And in current literature and in the current debates, there's a huge focus on the ontic version of structural realism. And also in my talk, I will only focus on the ontic version of structural realism. So what are motivations for ontic structural realism? The three most important and well-known arguments are the argument from coherence, the argument from parsimony, and arguments from underdetermination. According to the argument from coherence, our metaphysics should be coherent with our epistemology. So the claim is that all we can know is relational properties and not intrinsic properties, and since our metaphysics should be coherent with our epistemology, we should claim that all there is are relational properties. The argument from parsimony states that structure is all we need, in the sense of a plausible metaphysics can get along with relational properties only, but not with intrinsic properties only. So if our metaphysics should be as parsimonious as possible, then if we can eliminate intrinsic properties, then we should eliminate intrinsic properties. So in this sense, structure is all we need. Then arguments from underdetermination go mainly back to French and Lehmann, who state that there are cases of underdetermination in quantum mechanics that cast doubt on the existence of objects, but not on the existence of objective structures. And similar claims have been made with respect to general relativity. I would like to add a fourth argument. This is an argument that I call the transcendental argument, because in the philosophy of physics, one of the most important questions is, why is mathematics so successful in being applied to the world? And if Ontic structural realism is true, then this success is no miracle at all, because Ontic structural realism basically tells us all there is are structures, and mathematics, basically being the science of structures, would be a perfect explanation. So if the world only is structures, and if mathematics is the science of structures, then of course mathematics can be applied to the world. And the fifth argument, the fifth motivation, is the one that I would like to focus on in this talk. This is the claim that our currently best physics tells us that at the most fundamental of reality, there only are relational properties. And we will see that this means that our currently best physics tells us that moderate ontic structural realism is true. So I will discuss this and I will come to the conclusion that it is true for elementary particles only. It's true that elementary particles only have relational properties, but it's not true for quantum fields. And since I will argue that quantum fields are the most fundamental entities, I will argue that our currently best physics speaks against ontic structural realism. Okay. So let's talk about different versions of ontic structural realism. Perhaps the best known one is the radical ontic structural realism that goes back to what I was introduced by Lehmann and French. According to this radical version, there are no objects or individuals, there is only relational structure. So, for obvious reasons, this version of structural realism is called eliminative structural realism. One of the most straightforward objections is that there cannot be relations without relata. And the usual response by French and Lehmann is, and I quote, the relata of a given relation always turn out to be relational structures themselves on further analysis. Or to put it differently, it's relations all the way down. In my opinion, the main problem with this radical version is its eliminativist consequences that objects do not exist. So this means ordinary objects like tables and chairs do not exist, and also particles do not exist. And due to this radicality of this claim, it comes as no surprise that many researchers who feel sympathetic to ontic structural realism have opted for a more moderate version. So what is moderate ontic structural realism? Let's try to give a definition of this claim. So maybe the main idea is something like objects and structures are ontologically on par. There is no ontological priority. Lehmann defines it as follows. There are individual entities, but they do not have any irreducible intrinsic properties. Or, as he also states, all the properties of individual objects are relations to other objects. And Esfeld and Lahm, who are the main proponents of this moderate version, make the following claim, and I quote, "Moderate structural realism proposes that there are objects, but instead of being characterized by intrinsic properties, all there is to the basic physical objects are the relations in which they stand." Okay, so from the foregoing, I think we can differentiate between three claims. So the first one is what I call MOSR. This is the claim objects only have relational but no intrinsic properties. Then MOSR star, objects do not have irreducible intrinsic properties, so they can have relational properties, and they can have intrinsic properties, but only reducible intrinsic properties. So they cannot have irreducible intrinsic properties. And then what I call the most moderate version of Ontic structuralism, and what I think is the most tenable version, is the following claim, namely at the most fundamental level of physical reality, there are only relational properties. So MMOSR is the most moderate claim. If MMOSR is false, the other claims are false too. So I do not claim that modern anti-structural realists have to subscribe to exactly this claim, but I think that this is the most moderate version. If this claim turns out to be false, then all moderate versions have to be false. So here are some questions that moderate versions of Ontic structural realism have to face. First of all, does moderate Ontic structural realism collapse into the radical Ontic structural realism? Then what about ordinary objects like tables and chairs? What about particles? And this will also be a focus of my talk in the fourth question. Don't particles obviously have intrinsic properties such as charge, mass, and spin? So to tackle this question, we first of all have to get clear on what are intrinsic properties. And here the standard view is, and I quote, "Intrinsic are only and only those properties that an object has, irrespective of whether or not there are other contingent objects. In brief, having or lacking an intrinsic property is independent of accompaniment or loneliness." End of the quote. And here the classic example is mass versus weight. So the mass I have does not depend on where I am, does not depend on the other objects I'm surrounded with, but the weight does. So it is often assumed that mass is an intrinsic property and weight is an extrinsic or relational property. Yeah. So let's talk about ordinary objects. Let's talk about tables and chairs. According to the radical version of Ontic structural realism, ordinary objects do not exist. This is again a quote from French, and here I only quote the red part. There are no objects, thick or thin, and no identity, contextual or otherwise. So what does MOSR state about ordinary objects? So remember, MOSR is the claim objects only have relational but no intrinsic properties. So there are two logical options. First, ordinary objects do not exist, then it would collapse into radical version, or ordinary objects exist but do not have intrinsic properties. And in my opinion, also the second option is a little bit problematic, because you might argue that the mass of an object is an intrinsic property, but the shape of the table is an intrinsic property. The shape of the table does not depend on the other objects. And maybe the same is true for the mass of the object and the temperature of the object. So if we introduce now MOSR star, or strictly speaking we have already introduced it, but again, the claim is that objects only have relation, but no. So here the claim is objects only have irreducible. Objects have no irreducible intrinsic properties. This is the claim of MOSR star. Objects have no irreducible intrinsic properties. This gives us a third option. Now we can argue that ordinary objects have intrinsic properties, but only reducible ones. So you could argue, yes, the table has a certain temperature, but the temperature of the table is a reducible property or an emergent property. It can be reduced to the motion of the particles the table consists. And if you look at MMOSR, maybe the most modern version, then the consequences, it doesn't matter what properties tables and chairs have. It doesn't matter because tables and chairs are not the most fundamental entities. So it might be true that the shape of the table is an intrinsic property, but this doesn't refute this most modern version of Ontic structuralism because table is not the most fundamental entity of physical reality. Okay? So this is one objection of French. He states that modern versions of Ontic structuralism collapse into the radical version, so into his version of Ontic structuralism. So here's the quote. There is also the worry that if, according to MSR, so the model of structuralism, all there is to objects are the relations in which they stand, then there is nothing to the objects at all, and the position collapses into eliminativist Ontic structuralism. End of quote. And in my opinion, this is true for what we have called MOSR, but it's arguably not true for MOSR star, and it is definitely not true for this most modern version of Ontic structuralism. To see this, just consider the following example. So let's say the table has a certain temperature, or has a certain mass, and this mass is an intrinsic property of the table. And let's say this property is reducible to the underlying stuff. So if the temperature is reducible to the movement or the motion of the particles, and the mass is reducible to the forces. So the consequence is that radical Ontic structuralism has to state the table does not exist anywhere. MOSR states the table does either not exist or it does not have the intrinsic property of having this temperature or this mass. And MOSR states that the table can have this intrinsic property, but only if this property is reducible, only if this property is an emergent property. And again, MMOSR simply can state it doesn't matter. It might be true that this is an intrinsic property, it might be true that this intrinsic property is irreducible, maybe the shape of the table is irreducible, but it doesn't refute MMOSR. Okay, so I think we can skip this. And the point is that MMOSR does not collapse into the radical version of Ontic structuralism. And one point we could address is the question, do emergent properties even exist? Because there is some tendency in physics that certain physicists tend to argue that emergent properties do not really exist, but are only illusions or hallucinations. And if this is true, then it would make no sense to distinguish between MOSR and MOSR star. So this, of course, has to do with discussions in quantum gravity. So, for instance, where Uwe in the quote states, but unification of general relativity and quantum mechanics may well spell the end of time. By this I mean that it will cease to have a role in the foundations of physics. We shall come to see that time does not exist. End of quote. Okay, so here's the quote. And here's again a quote from Smolins, Lee Smolins. And this quote also shows his tenets in physics. So he states, and I quote, I believe that time is real and is essential for a fundamental description of nature. But I think it likely that space will turn out to be an illusion of the sort that temperature and pressure are, a useful way to organize our impressions of things on a large scale, but only a rough and emergent way to see the world as a whole. End of quote. So this is a quote that somehow shows that there's this tendency in physics to say that emergent properties are illusions or hallucinations and do not really exist. And if this was true, then it wouldn't make any sense to distinguish between the claim there are no intrinsic properties and there are no irreducible intrinsic properties. But this, of course, is highly counterintuitive, and I think most would agree that, for instance, temperature, even if it is an emergent phenomenon, is something that is real. And also, if you look at debates in philosophy of mind, most people agree that even if mental states like being hungry is only an emergent property or is a property that can be reduced to physical stuff, this does not mean that these mental states do not exist. I am hungry, whether or not this mental state can be reduced to more fundamental things. So this is just a side note of this discussion. And accordingly, I think that it makes sense to distinguish MOSR and MOSR star. However, we should keep in mind that the most tenable version is MMOSR. Claim that the most fundamental of reality, there only are relational properties. Okay, so let's come now to the main part of the talk, namely the question, does quantum field theory tell us that there only are relational properties, or does it tell us that there are intrinsic properties too at the most fundamental level of reality? Let's start with a quote from McKenzie, who states, and I quote, "Structuralists will hold that we need to look at the relevant physics if we want to develop a defensible metaphysics of it." End of quote. I totally agree with this claim, and I think virtually everybody who works on Ontic structural realism agrees that we have to look at the current physics. And also note that there's an interesting shift in argument. So at the beginning, with respect to epistemic structural realism, there was the claim that structural realism can avoid this pessimistic meta-induction claim. So there was this tendency of saying, okay, it's not so important what does current physics tell us, the point is the structure is the same, or we can know the structure and something like that. But now, with defending Ontic structural realism, there's this tendency of saying, okay, we have to look at the current physics, and then we have to see that it supports Ontic structural realism or not. And I totally agree with this tendency. And I also agree with the second claim from McKenzie, namely, and I quote, so we have now seen that, okay, we have to look at the relevant physics, but the question is, what is the relevant physics? And now I quote McKenzie, this is the framework of quantum field theory. And again, I totally agree with this claim. And then McKenzie in her paper goes on to show that particles, according to this framework of quantum field theory, only have relational properties, but this is the point where she stops. She does not talk about quantum fields. And I think that this is a problem because, in my opinion, quantum fields are the most fundamental entities, so we have to talk about fields. But first, let's talk about the mass, charge, and the spin of particles. Because philosophers of physics tend to agree that charge, rest mass, and spin are intrinsic properties. So a quote from Bird states, and I quote, "No one has suggested that charge, rest mass, and spin are not intrinsic." End of quote. And in this section, I shall argue that contrary to this common belief, the charge, the spin, and the mass of elementary particles are relational properties. They are not intrinsic, they are relational. But then I will go on and argue that fields have intrinsic properties. But first of all, let's have a closer look at quantum field theory. So, what are fields? Fields are physical quantities that permeate the whole universe and have a value at each point in space-time. And while classical fields have a numerical value, quantum fields have a quantum operator at each point in space-time. And quantum field theory basically is the result of marrying quantum mechanics with special relativity. However, the point is that this marriage, or this result, is not just a mathematical trick or a tool, but if you take it straightforwardly, it delivers new insights into how reality is structured. And by new insights, I mean insights that go beyond quantum mechanics. Okay, so taken seriously, quantum field theory tells us that particles are only secondary consequences and fields are the primary reality, quote from Wilson. And to be more precise, what it tells us is that for each type of particle, there is one underlying field of which the particles are excitations. This means all electrons in the universe, every electron in the universe is an excitation of the one and same underlying electron field with an all-encompassing quantum field. The same holds for photons. Every photon in the universe is an excitation of the underlying photon field. And so for all types of particles. So elementary particles are the excitations of elementary fields, and non-elementary particles like atoms are the excitations of of effective fields. So just some comment on the terminology. Instead of excitations, you also often hear claims like they are localized vibrations of field or the quantum of field. The idea, of course, is the same. Fields are fundamental, particles are secondary, derivative entities. Quote from Wallace. One immediate consequence of quantum field theory is that it can explain why elementary particles are indistinguishable, or to be more precise, why elementary particles of the same type are indistinguishable. So why are all electrons in the universe indistinguishable? They're indistinguishable because they all are excitations of the same quantum field, namely the electron field. And this is an explanation that can only be delivered by quantum field theory, not by quantum mechanics. So quantum mechanics gives you absolutely no hint why these elementary particles are indistinguishable, but quantum field theory has a straightforward explanation. And interestingly enough, such straightforward consequences of quantum field theory are seldom made explicit by physicists, and they are often ignored by philosophers of physics. And the debate concerning Ontic structuralism is just one example of this. And for Hobson, for instance, it is an embarrassment that physicists still fail to articulate that, and they quote, "The universe is ultimately made of fields." And this is also true when it is discussed whether mass is an intrinsic property or not. So, very often in discussion, when people claim that mass is an intrinsic property, they do not talk about the mechanism that completes the standard model, namely the Higgs mechanism. The Higgs mechanism completes the standard model by including one more field, namely the Higgs field. And it is popular to think that it is the Higgs boson that gives mass to the particles, but that's not true. It's not the Higgs boson, it's the Higgs field that gives mass to the particle that is responsible for this. So how does this work? The Higgs field, like every quantum field, is an all-encompassing field. It permeates all of space-time. And quantum fields, and this is crucial, they can interact with each other. They can couple to other fields. And some fields couple to some fields, but it's not true that the necessary couple to all fields. So as Tom Lincoln puts it, and I quote, "Some fields can see other fields by being blind to others," end of quote. And the photon field, for instance, can only interact with the fields of charged particles. So fields can interact with each other, they can couple to each other, but do not necessarily couple all of the other fields. And the photon field, for instance, only interacts with fields that have charged particles as excitations. And now the point is that the Higgs field has the property of giving mass to those fields that can couple to the Higgs field. And the particles which are excitations of the fields that couple to the Higgs field gain their mass precisely by the coupling, by the underlying fields coupling with the Higgs field. And this is also the reason why photons do not have mass. The photons do not have mass because the photon field cannot couple with the Higgs field. So let us now turn to the question of whether mass is an intrinsic property or not. Remember, how do we define intrinsic properties? Again, I quote, intrinsic are all and only those properties that an object has irrespective of whether or not there are contingent objects. In brief, having or lacking intrinsic properties independent of accompaniment or loneliness. End of quote. So is an electron's mass an electron's intrinsic property? Is the mass of an electron intrinsic property? Does an electron have mass irrespective of whether or not there are contingent objects? So obviously this is not the case. The Higgs mechanism explains why massive particles like electrons have mass and the electron would not have mass if the electron field would not couple to the Higgs field. And so the electron's mass is not an intrinsic property because it depends on the existence of other contingent objects. And the same holds for all massive elementary particles except for the Higgs boson and possibly for neutrinos. Now, what we have discussed already is that according to quantum field theory, fields are more fundamental than particles, and so you might have realized that for MMOSR, for this most modern version of Ontic structuralism, it doesn't really matter whether particles have intrinsic properties or not, because particles are not at the most fundamental level of reality. So what we have to answer is the question, do fields have intrinsic properties? Since fields are the most fundamental entities, the question is, do fields have non-relational properties or not? If they only have relational properties, MMOSR is true. If they have intrinsic properties, this means trouble for MMOSR. Okay, we have already seen that fields can interact and couple to each other. So this might suggest that all the properties fields have ultimately depend on their interactions with other fields. And this would render all field properties, all fundamental properties relational. And if this was true, then MMOSR would be true. However, in my opinion, there are at least two properties that according to our best quantum field theory, with the standard model, have to be intrinsic. The first property is the energy or the mass, or maybe more precisely, the vacuum expectation value of the Higgs field itself. We have already discussed that what distinguishes the Higgs field from the other fundamental quantum field is its non-zero vacuum expectation value. To be more precise, the Higgs field's vacuum expectation value is 246 gigaelectron. And from the Higgs field's equation of motion, it follows that the Higgs is stable only if it is non-zero, but its precise value is empirically finite. So why does the Higgs field have a non-zero value? Why has it the value it has? And this is a quote from Carroll. Indeed, the Higgs itself is a scalar field with mass, but it is not as if the Higgs gives mass to itself, it simply has mass, since there is no reason for it not to. And by the way, Carroll and Don Lincoln and A. Pops are all proponents of the claim that quantum fields are the most fundamental entities. So, what does this tell us? This means that the Higgs field has a non-zero value simply because it is what it is, and we do not know why it has the precise value it has. And since all the other fundamental quantum fields in the standard model are zero, the Higgs obviously cannot gain the property of being non-zero from the other fields. So we have mentioned that the electron field can couple to the Higgs field, and by coupling to the Higgs field, it gets energy, and this is the reason that electrons do have mass. But the Higgs field, according to the standard model, the Higgs field is the only field that has a non-zero value. So according to the standard model, there are 17 elementary particles, 18 if you want to include the graviton, And to each particle there corresponds an underlying field. So there are 17 fields, and the Higgs field is the only one with a non-zero value. So it makes sense, in my opinion, to claim that this property of having a non-zero expectation value is an intrinsic property, because obviously it doesn't get this feature or property from the other fields. So it has this property irrespective of whether or not they are contingent objects. This property is independent of accompaniment or loneliness. And this makes this property an intrinsic property. Exactly. So we have seen that since MMOSR is the claim that there are only relational properties at the most fundamental of reality, MMOSR is refuted by the standard model, since the standard model tells us that there are certain intrinsic properties at the most fundamental level of reality, namely, for instance, the vacuum expectation value of the Higgs field. And since MMOSR is the most moderate version of Ontic structural realism, irrespective of its precise formulation, is refuted by the standard model. And as I have mentioned, there is a second property that seems to be intrinsic for fields, and this is the field's spin. So when talking about spin, physicists mostly talk about a particle spin. But what is important for us is the commonly overlooked fact that a particle has a certain spin because its underlying field has such a spin. An electron, for instance, is a spin-a-half particle simply in virtue of its underlying field, the electron field, being a spin-and-a-half field. And again, a quote from Carroll: "The reason why this fact is so important is that each of the allowed spin measurements represents a new degree of freedom. That's physics speak for something that can happen independently of other things happening. Since we're really talking about here are quantum fields, every degree of freedom is a specific way the field can vibrate. For a spin-zero field like the Higgs, there's only one way it can vibrate. For a spin-and-a-half field like the electron, it can have two kinds of vibrations consisting of clockwise and counterclockwise spinning around whatever axis you choose." End of quote. So this means that the field's spin determines how this field can vibrate, and since according to the standard model, fields seem to have this property irrespectively of whether or not there are other fields, this property seems to be intrinsic and non-relational. And again, this implies the failure of MMOSR, and thus the failure of Ontic structural realism as such. So, of course, there are possible objections, and one possibility to avoid this failure of Ontic structural realism would be to introduce Ontic structural realism as the claim that particles only have relational properties. So you could argue that what we're interested in is not something like fields, what we're interested in only is particles. So we could introduce OSR particles as the claim particles only have relational properties. And we have seen that this claim, OSR particles, is true in the sense that all the properties particles have depend on the properties that underlying fields have. So they get the properties from the underlying field, and in this sense, OSR particles is true. But of course, this seems to be very much ad hoc and seems to be an unsatisfying way of reasoning. Because pointing out that there are properties, namely particle properties, that depend on more fundamental properties, namely field properties, and then ignoring the fact that at least that some of these fundamental properties are intrinsic and non-relational, doesn't seem to be an adequate line of reasoning in the favor of the spirit of Ontic structural realism. There are also, of course, other objections. So, for instance, one could argue that fields are not the most fundamental entities. One could argue that we should not interpret quantum field theory in such a way, or maybe one could argue that we shouldn't have such a focus on quantum field theory. And this talk definitely is not supposed to convince anybody who strongly believes that it is particles and not fields, to convince this person that it indeed is fields. So maybe Bromian mechanics is incompatible with such an approach to take quantum fields as the most fundamental entities. And then, of course, my talk will not convince this person. So what I want to try to show is that if we take quantum field theory seriously, if we take it straightforwardly, then it tells us that there are intrinsic properties at the most fundamental level of relativity. Because quantum fields do have intrinsic properties. Okay. So another possible objection would be that all what I've said might be true for quantum field theory and might be true for the standard model and for our currently best physics, but one might argue that quantum gravity will go beyond such a picture. So one might argue that this is only currently true, that in quantum gravity there will be an approach in which quantum fields will not be the most fundamental stuff. Or maybe they will be, but then they have no no intrinsic properties anymore. So what is quantum gravity? Quantum gravity is expected to be the next, and perhaps even the final revolution in physics. Like quantum mechanics and general relativity might revolutionize our understanding of the structure of reality. And of course, there are many motivations for quantum gravity. There are many conceptual reasons, also many technical ones. But the one I would like to focus on is that one could say that there's a dilemma of quantum physics. And this is because it seems that its two most fundamental and well-established theories, namely quantum mechanics and general relativity, cannot both be true on a fundamental level. In general relativity, gravity is a geometrical property of spacetime, and as the curvature of spacetime caused by matter and energy. Hence, strictly speaking, there is no force of gravity, and the gravitational field is a dynamical field, which means that there is no fixed background spacetime. Quantum mechanics, on the other hand, is formulated using a non-dynamical fixed background spacetime. And according to Rivelli, this means that accepting both theories means adopting a schizophrenic worldview. And the theory, still work in progress, that is supposed to find a way out of this conceptual misery, is dubbed quantum gravity. So basically, one might say there's a reconciliation of general relativity and quantum mechanics, but of course, it is only a very informal characterization of the definition of quantum gravity. So here we have a longer quote from Carroll. Basically, confirms what I've just said, namely that from the general relativist's perspective, gravity is not really a force at all. It does not act on objects. Rather than conceiving of gravity as a field that deflects objects from the initial path, general relativity allows us to understand that an object's inertial path is determined by the curvature of spacetime. This contrasts with quantum field theory, which is a theory of fields defined on a static background spacetime. Basically, the theory says that all matter is composed of particles which are understood as local excitations of quantum fields, so which is basically what I have talked about the last few minutes. And then, of course, there are many different ways how quantum gravity could work, and one is just to incorporate gravity into the framework of quantum field theory. So if this is the approach quantum gravity will take, then most of the stuff I have said might remain true in quantum gravity. With respect to the question of which road will quantum gravity take, French and Rickers state, so here I only quote the red part, that what is required is a background independent quantum field theory, or equivalent to quantum theory on a differentiable manifold. So, standard model, of course, is a quantum field theory, but one with a background dependent. There is background dependent. So, perhaps the most popular approach towards quantum gravity is string theory. And accordingly, we should talk also about string theory. Two quotes that might give a characterization of string theories. First, Kuhlmann says, and I quote, "The basic idea of string theory is not to take particles as fundamental objects, but strings that are very small but extended in one dimension. This assumption has the probable consequence that strings interact on an extended distance and not at a point," end of quote. And Schwarz states, and again I quote, "String theory arose in the late 1960s as a radical alternative to conventional quantum field theory, in which the fundamental objects are one-dimensional strings rather than zero-dimensional points," end of quote. So first of all, I think that these characterizations are problematic because they indicate or suggest that according to conventional quantum field theory, the fundamental objects are particles, or zero-dimensional points, namely particles. But as I have tried to show, conventional quantum field theory does not state that particles are the most fundamental objects, but fields. So, the difference between string theory and our current conventional quantum field theory is that according to string theory, strings are the most fundamental entities. According to quantum field theory, so according to the standard model, it is quantum fields whose excitations are particles. So, another quotation: "A string, whether open or closed, as it moves in space-time, it sweeps out a two-dimensional surface called a word sheet. String theory is a quantum field theory which operates on this two-dimensional word sheet with remarkable consequences in space-time itself and by in higher dimensions." So, what is a word sheet? First, let's have a look at the particle. The particle is a zero-dimensional object. It moves in space-time on this word line. The string is a one-dimensional object, and its movement in space-time is not described by this word line, but by a word sheet, two-dimensional word sheet. And if we think that this one-dimensional string is not enough, we can introduce a brain that is a two-dimensional object, or maybe a multi-dimensional object, and its movement in space-time then is described by this word volume. And according to the foregoing quote, quantum field theory gives us the necessary tools to treat the word sheets. So the word sheet might be handled within the framework of a quantum field theory. However, as I've already mentioned, this difference between string theory and our quantum field theory, in the standard model, it's often assumed that the difference is that the fundamental entities in string theories are strings, and in the standard model particles. But I think a better characterization would be strings versus fields. And even if we treat word sheets in the technical framework of quantum field theory, there remains the main ontological clash of strings versus fields. So maybe it would be possible to treat strings as excitations of fields. Then of course fields would still be the most fundamental objects. And if not, we have to tackle the question whether strings have non-relational intrinsic properties. This is not a question I can answer, it's not a question I'm going to answer, but maybe we can discuss this later. So just to give you an overview of what I've done, I've argued that we need quantum field theory in order to decide whether there are intrinsic properties at the most fundamental level of reality. Then I've tried to show that for particles it is true that they only have relational properties, but then I've argued that quantum field theory tells us that quantum fields are the most fundamental objects, and I've argued that there are at least two intrinsic properties of quantum fields, namely the non-zero expectation value of the Higgs field and the spin of quantum fields. Thank you very much for your attention.
So I will go general specific. So the general point is that I think your best version of Ontic structural realism is still ambiguous. So the ambiguity is about what you call the most fundamental level of reality. Mm-hmm. So you can read that as meaning the level of the most fundamental things, or you can interpret that as meaning the level of the most fundamental properties. Okay. And it seems to me that what the Ontic structural realists are interested about are not just about any property of the most fundamental thing. What they want to say is that the most fundamental properties of the most fundamental things are relational. So that's for general point. And when I go very specific, so your first argument, you consider the property of it is property of having non-zero value. So you talk of the most fundamental level of things, but the question is whether this intrinsic property of these things, the field, would also count as the most fundamental property of these things, and that's whatever you say is still an open question. I mean, superficially, this looks like having non-zero value looks like a disjunctive property to me, and on lots of accounts of what the most fundamental property are supposed to be, they are not supposed to be disjunctive properties. So superficially, they don't look like fundamental property to me.
Mm-hmm. Okay. Thank you very much for this this objection to this point. One problem with talking about the most fundamental properties, specifying what kind of properties these are, is that one could argue that maybe mental states are fundamental. So it's not true that mental states can be reduced to physical stuff, then it's true that my property of being hungry is fundamental in this sense. But this is not what modern Ontic structural realists want to talk about. And this is why I've introduced this claim as, so what I mean by most fundamental level of reality is, as you have pointed out, this first option, namely, what are the most fundamental objects, and do these most fundamental objects have intrinsic properties or only relational properties? Okay. And if this is not true, if it's not true that the most fundamental objects have only relational properties, so if you do have intrinsic properties, then I think any form of Ontic structural realism is true.
Okay. My impression was that the Ontic structuralists can accept that there are they can accept that the fields are the most fundamental entities.
Yeah.
They can accept that these are intrinsic properties, but they can also say, well, look, these intrinsic properties emerge on relational property of these things, and that will still count as an Ontic structural realism. And that's the kind of view you want to block. And so, I don't think you said anything to block this.
So you would say that the argument has to be that the most fundamental objects only have non-reducible intrinsic properties.
That's what you have to show, yeah. It seems to me.
And you would say that having a non-zero expectation value is reducible to what?
It looks disjunctive to me. It looks like having either, I don't know, 0,1, 0,2, 0,3. And for me, it looks disjunctive. And if you think that disjunctive properties are non-fundamental, then that wouldn't turn out fundamental. But it doesn't look relational either. It looks
but if it's an emergent property, it has to emerge from somewhere. And if the fields are the most fundamental stuff, where do these properties emerge from?
Well, on specific values, not on just having non-zero 1. Just having, I don't know, 0, 1, 0, 2, 0, 2.
Okay.
So let me ask Chicago to ask the next question. Keizo?
Yeah, okay. So what I'm going to discuss is the things you said about springs in the end. So I think you should be aware that people have tried to develop string field theory, and thus describe strings more analogously to how particles are described in quantum field theory. At the current way it's typically described, we don't do that. While we have field theory descriptions on the world sheets, the individual strings are not kind of described in terms of this deeper field. But in principle, I think people would assume that that would be possible. So there is no kind of strong conflict there between these two things. And then I think even though you kind of criticize this point that people say, especially physicists say, particles are replaced by strings and just describe particles as most fundamental. Of course, typically the physicists aren't really interested in those kind of what's most fundamental and what's kind of this thing. So it might be kind of more loosely put if it's physicists saying this, and perhaps the best way of saying it is just like what corresponds to particles in the old description corresponds to strings in the other one. And then that's kind of a neutral way of reformulating kind of reading what physicists say. Because I don't think many of those kind of have any kind of deep metaphysical use when they express it. They just kind of express it.
They may well mean like in Feynman by accident, right? So in the perturbation scheme, it seems exactly true. Place particles, surfaces without, as you say, kind of deeper ontological.
Exactly, but many would still expect that there will be kind of a deeper string field theoretic descriptions. So I wouldn't read the physicists as making that claims. That's kind of
Okay, thank you very much. But of course, this has important metaphysical consequences. So there's the one claim, string theory claims the most fundamental objects are strings, and the second claim is string theorists claim that what we now treat as particles has to be replaced by strings. Because the difference is then, as you have pointed out, and we could say, okay, it's still fields that are the most fundamental objects, and these fields have excitations, and these excitations are not particles, are not zero-dimensional particles, but one-dimensional strings, or maybe multi-dimensional brains or something like this. And this, of course, has important metaphysical consequences. So,
Wow.
I think you can agree on that.
No, I mean, there is metaphysical difference what the world is like.
Yeah.
If string theories versus if quantum field theories. But I wouldn't say that there is a difference between, say, should we have should we have on the one hand a string or particle ontology that's like one side, or should we have a field ontology? I think you're pushing a field ontology interpretation, which I think is fine. And I think that is still compatible with the string theoretic description.
Okay, perfect.
And what I was saying basically is that physicists say certain things like that. They don't really care about metaphysical things. So you shouldn't kind of read them as being kind of making strong claims about particles are really the most fundamental thing. Because many of the people who would say more fundamental particles are replaced by strings, if you push them in a kind of, and actually want to push them into metaphysical discussion, I wouldn't be surprised, at least many of them would say, if you ask them, wouldn't you say that the fields in quantum field theory are more fundamental than the particles? Many of those would probably agree, but still kind of just describe it like that way, say kind of the fundamental particles are replaced by strings. Because they don't really worry about these issues in the same way as metaphysicians would do. So that's kind of a way of so I'm not kind of criticizing the idea of pushing a field ontology line, and I'm also saying that's probably compatible with the string theory as well. What I'm saying is that you should really lean into what physicists say when they kind of loosely describe these things.
Okay, thank you very much. Perfect.
Thank you. I have two questions. The first is maybe more methodological. It's about the beginning of the talk, about I wasn't sure I understood the connection between. It seemed to me that you mix two things, and maybe I don't understand what the connection is between the two debates. So we have the first debate about what are the relata of the relations at the fundamental level. And so you have the radical version which says that there is nothing.
The only structures.
And so I think, so you have this question, what are the relata? And then you move on to macro object, ordinary objects. And I wasn't sure about the connection between the two debates because to me it seems that you can have different answers to the first debate. It's completely disconnected from the second question, namely whether ordinary objects exist or not, whether they should be reduced or eliminated. I mean, why do you think that there is no pressure for the radical version to accept that ordinary objects are not real?
Okay. So yeah, it's true. The radical version, the radical anti-structuralism claims none objects, there's only structure. And one consequence of this claim is, of course, that there are no ordinary objects. So the other consequence is there are no power.
I don't get this, of course. I don't understand why not identify, like the table is just identical to this piece of reality, this relation all the way down. I think there is room for this position.
I mean, they reconceptualize ordinary objects in terms of structures. But still, this table does not really exist in the sense of it's an individual object, but it only is structure. It has to be reconceptualized in structures. And I think that maybe one shortcoming of this radical version is that it somehow, maybe this is the point of issue, that this formulation is somehow strange or ambiguous and it's not so easy to understand what it's supposed to mean. So I think that the talk about intrinsic and relational properties captures this whole debate better because it's clearer what is meant if you say there are only relational properties. So I think that if you talk about, I think that one of the benefits of the moderate Ontic structuralism is that this whole debate makes more sense if you talk about are there intrinsic properties or are there only relational properties. I think that this talk makes more sense than saying is there only structure or are there individual objects. And if we claim that there are intrinsic properties, that at least we claim at the most fundamental level there are intrinsic properties, then any form of Ontic structuralism is the moderate version and also, of course, the radical version.
So if I may just try to press a bit the point, maybe try to put it like that. What does it change to say that the table in front of me is made of particles, of fields, or of relations, all the way down? I mean, it just seems that. I mean, that's, I guess it's something to.
I mean, of course, you could say that also according to quantitative physics, the table is, of course, a fundamental object, but it's an emergent object. It emerges from the part it consists of, and the fields and the forces that are at work here. But the difference is that according to this emergent picture, the table is still a real object. It is still an individual object that emerges from the more fundamental level. But according to the radical structuralists, this table doesn't really exist. It's only a structure.
I mean, maybe we will put in that discussion later. And I have another question, maybe later.
Maybe later, yes. Another question from Chicago, Nick?
Yeah, hi. So this was going back to the discussion of quantum field theory. I guess wanted to push in sort of two directions. One was to suggest some other properties that seem like they might be intrinsic to me, and the other, well, I'll come to that in a minute. So you didn't mention charge. I didn't quite know why that didn't end up on your list. But there's also something else. When physicists talk about these about intrinsic properties, they have, I think, sometimes something different or more in mind than the kind of philosophical definition you gave. They actually mean classical, non-quantum, constant properties, C-number properties, when they list their intrinsic properties, which is, I think, a different notion. So let me give you a non-sort of C-number property that seems like it could be intrinsic to me as well, for a field which is something like total particle number, the expectation value of the particle number. I don't see why that would depend in any way on the existence of fields. That seems like an operator that just counts how many excitations there are. It may not be a definite number, but there's still an expectation value for that. So that seems like it will be intrinsic. I think I already mentioned charge. Yeah, and then other observables seem to be then that they might end up being intrinsic. I guess on the other side, I wanted to. You didn't really. You cited Kerry McKenzie's paper, but I was just going to mention she does have some arguments that some of the. I can't remember. Isn't spin on her list of things she tries to argue? It's
in her paper, she argues for, in particular, that charge is relational, but only. But as far as I know, and as far as I remember, she only talks about the properties of the particles, not about the properties of the fields. So she gives an argument why particles, and in particular the charge of particles, is relational and not intrinsic, but she does not talk about quantum fields, or at least she does not talk about the properties of quantum fields.
I think, okay, I have to look at the paper again. I seem to remember taking that, that just to be sort of physicists talk about the particles. I mean, they're talking about the C numbers that characterize the fields, I thought. But I don't know, you maybe looked a bit more, more recently. If you're talking about the number of particles or the charges, I mean, you are talking about the mathematical space that characterizes the field. Anyway, let me go back to the other point. When you think about, total particle number or excitation number of a field as an intrinsic property of the field.
Thank you very much for this. The more reasons we have that there are intrinsic properties, and the more intrinsic properties there are, the better it is for me. The better it is for this argument that at the most fundamental level of reality, there are intrinsic properties, namely properties of fields. And I focused on the vacuum expectation value of the Higgs field because they are most confident in, and also because first I talked about why the mass of particles is not intrinsic. So what you add to this list is perfect for me, and so of course I have to think about it in more detail, but prima facie this seems plausible to me to say that, for instance, the excitations of the fields are intrinsic because they do not depend on the other fields, on the existence or the interactions with other fields.
Okay, and I just wanted to make that more general point that physicists, I think, isn't this right, Kaiser? I mean, when they say intrinsic qualities, they don't mean the thing that you mean by that definition. And so I think there is a kind of miscommunication sometimes between philosophers and physicists on that.
Of course, So if, for instance, Carroll says there's an intrinsic property, we have to reflect on what does this mean. But if it means, or if it includes, that this field has this property irrespective of whether or not there are other contingent objects, then it's precisely what I care about.
Do you have any questions here? Can I just say a bit more of an editorial remark about your use of, most fundamental? I guess when you started calling quantum field theory most fundamental, I started thinking, what about string theory? That's more, how can quantum field theory be the most fundamental? Surely string theory is more fundamental. In fact, hoped to have a string theory for 20 years ago, people hoped to have sort of string theory would be the unified theory that in fact explained the values of all these C numbers. And so, you don't really mean most I found that a little funny about most fundamental.
Yeah. So when I talk about most fundamental, I mean most fundamental according to our currently best proved theory, and this is of course the standard model, at least with respect to particles. So I do not talk about spacetime, I do not talk about spacetime structuralism, but I do talk about particles and fields and whether there are intrinsic properties in this area. And then I talk about the most fundamental level, I talk about the most fundamental objects according to our currently according to the standard model. So about fields.
So MMOSR kind of needs a little subscript or something to tell you, what theory we're talking about as being most fundamental or something like that. Is that
Yeah, I mean, you can make many different arguments. You could argue, okay, you could write a paper about what does string theory tell us about intrinsic properties, but that's not the topic of my talk. The topic of my talk is what does the standard model tell us about intrinsic properties, and this is, in my opinion, that quantum fields do have intrinsic properties, and this means trouble for Ontic structuralism. Of course, Ontic structuralism could claim quantum field theory, at least the standard model, is not the most fundamental level. It will turn out that it's string theory, but that's another topic. It's not the topic of what I've cared about. So I've tried to give some hints what might happen with string theory, but of course, this will not be a part of the paper because this would explode if I would talk about old approaches to quantum gravity that might turn out to be more fundamental than the standard model. So I only try to show what does the standard model tell us about intrinsic properties at the most fundamental level, and here the most fundamental level is quantum fields.
I have a thing. I have a finger on this, just a finger. I mean, even if you don't go beyond the standard model to the really fundamental physics, quantum gravity, even if you stick with established physics, then there's a perfectly respectable sense in which general relativity is just as fundamental as the standard model, because it's both has to be part of the fundamental thing that you're given from which you can derive everything else, because otherwise you just don't have space-time.
So all I have said is totally compatible with the view that space-time structuralism is true. So I have only talked about fields and particles. Yeah, that's true.
Fair enough. Yes,
thank you for the talk. I have several comments, but maybe the first one is, the main one is, how do you see your questioning? How do you see your arguments in the light of the different ambiguities in QFT? Because you said basically, as I understood you, that structuralists should be more serious about the QFT and really look at what QFT is about. QFT is about field, about your argument, and field have intrinsic properties. Now, I think it's not true that they haven't looked seriously at QFT. Some people have explicitly exploited these ambiguities, like in representation, in the mathematical sense in QFT, or the fact that QFT is a quantum theory in the end. So all you said makes sense only if you say something about the ontology of the theory, and in the sense of saying something about a coherent ontology, in the sense of in light of the Neumann problem, for instance. And you did mention the wall mechanics, for instance. So how do you see your arguments in the light of these ambiguities? Because there are two levels in your argument. Either you just look at the standard model as written in textbook, or you're looking at fundamental theory in the sense of a well-defined QFT, and this is not an issue then. So what is your argument?
So one of my points was that very often when physicists or philosophers talk about intrinsic properties, they do not mention quantum field. So for example, those people who say that the mass of particle is intrinsic and that nobody has to challenge this and there's no reason to challenge this, I think we should challenge it if you look at the Higgs mechanism. And that what you have said, that there are many proponents of anti-structuralism who care about quantum field theory. This is true, and I would not object to this. And one example is, for instance, Kerry McKenzie, when she talks about quantum field theory and tells us, okay, quantum field theory is the framework that we use, and she wants to decide whether according to this framework there are intrinsic properties or not. But then, and this is how I have this remember this paper. This is also how I think most people who work on this reason is that then they talk about particles only, not about quantum fields. They talk about the properties particles have, but they do not talk about the properties quantum fields have. And I think if we interpret quantum field theory straightforwardly, precisely in the way like Carroll and Don Lincoln and so, then we come to the conclusion that we shouldn't treat particles as the most fundamental objects but fields. And if you look at two fields have intrinsic properties, then I've tried to show that there are reasons to believe so. So this interpretation is interpreting quantum field theory in a straightforward sense. And of course, as I've mentioned, if you are a proponent of Bromian mechanics, you will not be I will not be able to convince you, because this talk is not about convincing you that quantum fields are the most fundamental objects. This talk is about, if we presume this, like many people do, then the consequence is that at the most fundamental level, there are infinite properties.
Yeah, but on the other hand, all the arguments you've been given are only in the free sector.
In which sector?
In the free field sector of the theory. So either you give me a clear ontology of what quantum field is, and then we can talk about the intrinsic properties of those objects and so on, or you define precisely what kind of theory you're looking at, because.
Okay. It seems to me that when proponents of anti-structuralism talk about particles, they also don't give you an explanation of why are particles the most fundamental objects.
Yeah, but then it's bad philosophy. But if you look at what the theory says, or what are the features of the theory, then you can build arguments on this. But my question is more about how do you see again your argument in the light of the ambiguity of the theory? Whether you just stick to the textbook QFT.
Yeah.
Because, for instance, the issue about inequivalent representations and the correct way of formulating the theory has been exploited by structuralists in order to argue for a structuralist understanding of quantum fields. Not mentioning of particles, of course.
So to stick to the claim that quantum fields are more fundamental, but claim that they only have relation properties?
Yeah.
In which, okay. So you would
I'm thinking, for instance, just Stephen French's argumentation on the use of algebraic structures and inequivalent representations and so on.
But I mean, to refute anti-structuralism, it is enough to point out that there's one intrinsic property.
But again, that's the point. To the extent that this intrinsic property really is a fundamental property according to the theoretical framework, because the property you're mentioning is only well defined in the non-interaction sector of the theory. So a deeply non-fundamental sector of the theory, because of course we have, it seems, an interactive world. You see what I mean? Either you define clearly the framework, the theoretical framework within which you are working, and then you say in this framework it seems that I have identified an intrinsic property, and then therefore OSR might not be a good interpretation for this sector of the theory. Or again, this question of most fundamental and so on, or at the most fundamental level, again, to be defined in the theoretical framework, but let's take QFT. OSR is not a correct interpretation, but if it's the latter, then I think it's not entirely sound.
Okay, but if you look at the concrete feature, concrete characteristic, or concrete property, like, for instance, this property of the Higgs field, you have a non-zero expectation, a non-zero vacuum expectation. So you would say that in certain frameworks, this property is intrinsic, in certain properties, and certain frameworks it is not.
I'm just wondering that if you say at a more fundamental level, in the sense that you're just talking about a free field, and the real world is about interacting fields, these people might give you a structuralist account of the main features of the theoretical framework, because we don't have a nice ontological picture at this level.
Okay. So, but still, I don't see how this interacts. So, of course, the world we live in, the fields interact with each other. But I don't see how this expectation value somehow depends on this interaction.
But because this would be only a high level property. It's something you basically measure at infinity, strictly speaking.
Okay, maybe. Yeah, but did we continue that particular conversation over here, Lorenzo?
Yes. I had a question about which was suggested to me by the fact that you insisted very much on the idea that you should take quantities seriously and you should take it straightforwardly. And I had a question on this straightforward. Because when you ask a physicist what a quantum field is, they will answer something is a mapping of functions between spacetime points and operators. We talk about operators. Well, if you take that literally, the fundamental objects need to be well, these mappings and the operators and states and all of these things. And so you can say that all the properties of a field are so defined. Well, the operation means what it maps to, the kind of operators it maps to, the kind of point. So my question is, one option is A, well, don't take that seriously. It's kind of a confusion. Don't take this description seriously. Or B, well, explain what is a field that is not really a function between points and operators.
Yeah, but if we talk about, maybe it's easier to talk about, so let's start with the classical field. The classical field is a physical quantity that permeates the whole of space and has a numerical value each point in space-time. Would you say that this is enough, that this whole object only has relational properties because it has values? I don't see why it should be something, why it should only have structural properties simply because it has a value at each point. And similarly, the quantum field doesn't have this value, this numerical value, but has this quantum operator at each point. So I don't think that this makes the whole object an object that only has relational properties.
Well, you describe it essentially by a relation between the points and the operators. First of all, my point was that, well, it's not clear that on the face of it that the most fundamental object are the fields, or not just the fields, these operators. If you take a line, say, the line of Quine, and you say, well, what do I quantify over such theory? Well, I quantify over a lot of things, which are not just the fields. So I have operators, I have states.
I'm not sure about this because we think again about the classical field to say that it has a numerical value at each point doesn't mean that the numerical value is more fundamental than the field.
Well, no, it doesn't. Of course, I didn't mean to imply that the operators are more fundamental than the fields. They're just as fundamental.
Anyway, that is what the quantum field is.
Well, if it is, then I guess I would say this is kind of pretty relational. Since it's just a relation. What it maps what to what. Pretty much what it is. Pretty relational.
Okay, Philipp?
Yeah, it's about some clarification regarding the Higgs boson has mass not intrinsically, but only the field has because the particle depends on the field. So, for it to come out extrinsic in the Lewis definition cited by Esler and Long, the two things, well, the thing it depends on has to be mereologically distinct. And I'm really just wondering, this talk about excitations and so on, is the particle meteorologically distinct from the field?
No.
But then the dependence on the existence of the field doesn't make the property extrinsic.
Yeah,
At least in the standard definition.
I mean, strictly speaking, I haven't said that the boson gets the mass from the. Sorry, strictly speaking, I didn't say that the Higgs boson gets the mass from the Higgs field, because very strictly speaking, this would be false. What I said is that the electron gets the mass from the Higgs field, because all the electrons in the universe get the mass from the Higgs field, because the underlying electron field couples to the Higgs field. And so the Higgs field gives mass to the electron.
Okay,
And so there are two distinct entities, there's the electron and there's the Higgs field. In this sense, in this relation.
Okay, no problem with that, but there was also this further argument that the particles, they kind of have the intrinsic properties, the fields that have the intrinsic properties, because the particles depend on the field. Now, if they're not meteorologically distinct from the fields, then that argument is
That's true, that's true. So, that's true, yeah. So, this MOSR particles that I've introduced, which is not my position, but what would be a seeming possibility to object, make an objection against value. Strictly speaking, this claim is somehow strange because, as you have pointed out, the electron field are not totally distinct. The electron is, in some sense, this field. It's an excitation of the field. So to say that the electron gets all its properties from the field is somehow strange, but it's not important for the question of MMOSR, because this most modern version states that we care about the most fundamental objects, and these most fundamental objects are not the particles but the fields. So, I mean, it's true, it's strange because the particle, in a certain sense, is part of the field, but I don't think that this is a problem for my argument that fields have intrinsic properties. But it's a very good point.
Okay, there's one last question from Chicago. Nick?
Yeah, so thinking about the arc of the talk and how you set things up, at the very beginning, where we were talking about scientific realism, I just wondered if the ends of the talk kind of connect up. I mean, it is part of the idea here, well, look, there are intrinsic properties in quantum field theory, and so quantum field theory is, subject to pessimistic meta induction. Ontic structuralism won't get us out of pessimistic meta induction because there are intrinsic properties. Is that what you think?
Yeah, I think this is absolutely true. I think the way structuralism has been introduced by Borel was, one idea was to avoid this pessimistic meta induction. And of course now the direction we are going with Ontic structuralism does not care about avoiding this anymore because it depends on interpreting our current best physics. So this is true, there is a shift in the argument. At the very beginning with the epistemic structuralism, there was this goal of avoiding the pessimistic meta induction and still being able to explain the success of science. But now in the debates about Ontic structuralism, these debates very much depend on interpreting our currently best physics. So they do not avoid the pessimistic meta induction. That's true.
So more concretely, there'll be more fundamental theory that doesn't have the Higgs, and so now you can come and say, see, you were wrong about the Higgs. You should be kind of.
Absolutely true. Absolutely true.
Okay. Thanks.
Well, with that, we've come to the end, and please join me in thanking Philipp once again.
Thank you.
Okay, and thank you, Chicago. Bye-bye.
Bye, everybody. Have a nice dinner.
Have a nice lunch.